In this video, we will explore the complex relationship between time symmetry and asymmetry in the context of the laws of physics, and examine the nature of time as both a fundamental and enigmatic element of our reality. We will attempt to do this through the complex interplay of temporal dynamics, symmetry, and the fundamental forces that govern our universe. Let's start by comparing the second law of thermodynamics to other fundamental laws of physics. The second law is not symmetric concerning time, while most other physical laws are. Time symmetry, or T-symmetry, implies that the laws that govern physical events are invariant when time is reversed. Equations such as Newton's laws, Hamilton's equations, Maxwell's equations, Einstein's general relativity, the Dirac equation, and the Schrödinger equation exhibit this time symmetry, which functions the same regardless of whether time is running forward or backward. This symmetry implies a kind of timelessness or reversibility found in most physical processes, with the obvious exception of thermodynamics. The second law of thermodynamics introduces a fundamental asymmetry known as the arrow of time. This law states that entropy, or the measure of disorder in a system, tends to increase in a closed system. This increase in entropy is directionally tied to what we perceive as the forward flow of time and distinguishes it from the reversible processes described by the other equations. While symmetry often represents balance and equilibrium in physics, asymmetry is essential for change and dynamism. In cosmological terms, symmetry breaking is a fundamental concept. It is responsible for the emergence of the four fundamental forces: electromagnetism, the weak force, the strong force, and gravity. These forces emerged as a result of symmetry breaking in the early universe, and they demonstrate that asymmetry is as important as symmetry in the laws of physics. The proposed idea is intriguing. If symmetry breaking can give rise to fundamental forces, could a similar mechanism govern the emergence and flow of time? This speculative leap opens up a discussion about whether our experience of one-way time, aligned with the arrow of entropy, is merely a subset of a larger temporal structure that also includes a backward flow. The concept of temporal symmetry also depends significantly on perspective. Outside the flow of time, we can imagine an external perspective from which forward and backward time would appear coextensive and symmetrical. From within the flow of time, however, our experience is asymmetry. Time appears to move from the past to the present and into the future, consistent with the second law of thermodynamics. However, if one shifts perspective and imagines time as moving backward from the future to the present, symmetry is restored. This thought experiment challenges our intuitive understanding of time and suggests that the asymmetry we experience may be a result of our being embedded in time. Time symmetry is therefore proposed as a relative rather than absolute phenomenon. It is a perspective-dependent property of our universe. This model suggests that forward and backward time can coexist simultaneously rather than mutually exclusive. This concept challenges the traditional dichotomy of past and future, suggesting a more complex temporal reality in which both aspects of time are intertwined and potentially indistinguishable. If time can flow in both directions, how do we understand cause and effect? Would free will retain its meaning in a temporally symmetric universe? Or would the concept of reverse causality require a reevaluation of our understanding of action and effect? Given that our experience is tightly aligned with the forward flow of time, practical difficulties arise in testing the hypothesis of temporal symmetry. Our subjective experience is a limited perspective on a larger temporal reality, just as entropy represents only a subset of possible temporal dynamics. This invites speculative thinking about whether time backward might manifest in subtle, undetectable ways within our current understanding of physics. Certain quantum phenomena, such as wave-particle duality and entanglement in the double-slit experiment, are better understood when considered within a framework that allows for temporal symmetry or reverse causality. The idea that particles can operate in a realm of timelessness or reverse causality means that their seemingly paradoxical behavior can be reconciled by accepting a richer concept of time. More robust mathematical formulation and experimental demonstration are needed before the idea of temporal symmetry can be extended beyond the realm of metaphysical speculation. To show that time may not be strictly one way at the quantum level, it is necessary to examine fundamental concepts and theoretical frameworks, such as Feynman diagrams and the role of virtual particles. This discourse opens a path to rethink causality and the flow of time in the light of quantum mechanics. It is suggested that temporal reversibility may be an inherent feature of quantum mechanics for certain quantum theories. This concept is first demonstrated through Feynman diagrams, which are graphical representations for depicting particle interactions in space-time. Feynman diagrams usually represent quantum interactions involving particles and their corresponding antiparticles. In addition, quantum foam is an idea derived from quantum field theory, in which space-time at the Planck scale is not smooth, but is filled with transient energy fluctuations. These fluctuations constantly appear as virtual particles. Due to the Heisenberg uncertainty principle, these virtual particles cannot be observed directly, but they contribute significantly to the fundamental structure of space-time and quantum fields. In the context provided, a particle and its antiparticle can emerge from this quantum foam and annihilate each other almost instantaneously, a process illustrated by the dots on a Feynman diagram. This depiction forms the basis for the discussion of time symmetry. A particle is often depicted as moving forward in time, while its antiparticle is often depicted as moving backward in time. We will explore a scenario in which an antiparticle is thought to be moving backward in time, which provides a compelling picture of temporal oscillation. Creation and destruction points are treated as turning points where the direction of time appears to reverse. In this framework, the particle oscillates between moving forward and backward in time, similar to a standing wave oscillating between the two states. This conceptual model opens up the possibility that a particle-antiparticle pair may exist in a kind of temporal superposition in which the distinctions between forward and backward in time become blurred. This is not just a mathematical abstraction, but an actual feature of the quantum world that may hold deeper insights into the nature of time. Feynman diagrams do not just serve as computational tools. They provide a visualization that allows physicists to consider time from a unique, timeless perspective. In these diagrams, a frequently used convention is that arrows pointing forward in time represent particles, while arrows pointing backward represent antiparticles. This depiction lends itself to an interpretation in which antiparticles could be particles moving backward in time. If time is just another dimension, like space, then under the right conditions it may be just as possible to move backward in time as it is to move in a different spatial direction. As Paul Davies points out, let's refer to the idea proposed by John Wheeler that there could be a single electron in the universe, constantly moving back and forth in time, creating the illusion of many electrons. Similarly, photons may exhibit a special relationship to timelessness, contributing to their apparent wave-like or particle-like behavior depending on the observational context. This speculative idea is compatible with the concept of quantum temporal oscillations, in which particles are not strictly bound to a single temporal direction. Instead, they exist in a state that oscillates between past and future, fundamentally challenging our traditional notions of time and existence. We will look at a theoretical framework known as the two-state vector formalism, developed by Aharonov and Weidmann. This formalism suggests that a complete description of a quantum system requires two state vectors, one evolving forward in time from the past and the other evolving backward from the future. This dual description provides an objective account of phenomena such as entanglement and the EPR paradox, for which traditional notions of causality seem inadequate. Although this approach has been under-researched and not widely adopted, largely because of the controversial implications of reverse causality, it opens a fascinating dialogue about the fundamental nature of time and its potentially two-way character at the quantum level. We can then pose a provocative question. Can these quantum-level temporal oscillations extend to the macroscopic scale? Could our perception of time as a one-way flow be replaced by a model in which time oscillates simultaneously between the past and the future? This perspective challenges the deeply entrenched notion of linear time and suggests a more fluid understanding of temporal reality. If time at the quantum level is not strictly linear and oscillates, this could have profound implications for our understanding of causality and the structure of reality. We will examine the concept of space-time elasticity, the curvature of space-time that is central to the theory of general relativity and is defined in terms of time and light propagation. In this context, we will discuss the implications of gravitational lensing, geodesics, light cones, and the concept of time reversibility, and provide a framework for thinking about how the curvature of space-time affects our perception of time and events. General relativity assumes that massive objects cause space-time to curve, and that this curvature is what we perceive as gravity. One observable manifestation of this curvature is gravitational lensing. Gravitational lensing occurs when light from a distant object passes near a large object, such as a galaxy or a black hole, and its gravitational influence bends the light. The bending of light paths can cause the distant object to appear multiple times around the larger object, creating the illusion that the hidden object is located on different sides. The discussion proceeds by clarifying a critical concept. The straightest path in space-time, known as a geodesic, is not necessarily a straight line in three-dimensional space. In a curved space-time, a geodesic is the path that a particle or photon takes to minimize its action and corresponds to the straightest possible path given the curvature of space-time. This is analogous to the shortest path between 2 points on a curved surface, such as a sphere. On a two-dimensional map, the shortest path between two locations may appear as a line, but on the three-dimensional surface of the Earth, a sphere, this path is the straightest. It is a geodesic. Similarly, in the context of gravitational lensing, light from a distant star is bent around a massive object, not because it follows a curved path in the traditional sense, but because it follows the straightest possible path in curved space-time created by the gravitational field. The concept of light cones has been introduced as a critical tool for understanding the causal structure of space-time. A light cone represents the set of all possible paths that light can take in space-time and result from a single event. In a space-time diagram, the vertical axis represents time, while the horizontal axes represent spatial dimensions. The light cone consists of two parts, one that opens downward, representing all possible past light trajectories leading to the event, the tip of the cone, and the other that opens upward, representing all possible future light trajectories that could have emanated from the event. Light cones embody the concept of causality in relativity. Inside the light cone, events are causally connected. They can affect each other within limits determined by the speed of light. These are called temporal intervals, and two events occur at the same spatial location but at different times. In contrast, outside the light cone, there are spatial intervals in which events occur simultaneously but at different spatial locations, implying that there is no causal connection between them according to special relativity. One consequence of the light cone structure is the idea that photons are timeless, or exist outside of the conventional flow of time. Since photons travel at the speed of light, they always travel along the boundary of their light cones and do not experience a proper passage of time. The concept of time for photons is fundamentally different. They do not have a time-like existence. This means that, from the photon's perspective, the journey from one point in space to another is instantaneous. There is no before or after. This insight raises interesting questions about the nature of time and existence. If photons do not experience time in the same way that massive particles do, they could be thought of as timeless entities. Light cones are typically depicted as upright in flat spacetime, but will appear curved when considering curved spacetime, such as near a massive object that causes gravitational lensing. This curvature represents the curvature of spacetime itself. Under a curved coordinate system, light cones appear to bend and curve to reflect the curvature of spacetime. This visualization helps to understand how gravitational fields affect the passage of time and the paths of light and other particles. This curvature is often viewed as a coordinate effect, that is, it is due to the choice of how we define spacetime rather than representing the actual physical curvature of the light paths themselves. However, this curvature becomes more important when considering more exotic spacetime structures, such as those involving time loops or closed time-like curves that suggest the possibility of paths returning to their starting points in spacetime. Thanks for listening. Take care.